First of all, thank you for coming. I will be honest with you. I wouldn't have been surprised, the least, if the room would be empty. I mean, it's security nightmares. I mean, we're talking about one of the two major events. And I'm really, really flattered by the attention. So, I see we do have an issue there, because, nope. Boom, boom, boom. That's screen number 8. Sorry. You know how stuff works, don't you? And of course, I am in the wrong folder. So you will see me doing some command line fill. Boom, boom. Oh, come on. 31C3. Presentation. So this is the main part where I explain to you how you start a presentation over the command line. And here we are. And this thing's great. I think we do have to solve that problem here. I do have to... I'm sorry. Okay. That's how things work. Boom, 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 boom. 31C3. Presentation. So, yeah, as you have imagined, it's about making your own telescope. I will brabble along because I'm here. That's kind of, yeah. Do you know, I'm sorry, I just screwed up, totally.
Don't worry about it.
I think you're not live.
Yeah, I don't think so either.
So, he told me not to worry about it.
Yeah.
I mean, I don't, to be honest, I don't have to worry about it because I already screwed up.
Yeah, but it's the last day of Congress, it's the last talk. We had 4 days of not much sleep, probably.
Yeah, tell me more about that.
And we are all hackers, so we love terminals, and why not just look at them for a few minutes?
So, yeah.
Just to appreciate the beautiness of green fonts on black backgrounds. Oh yeah, yeah.
So if you want to poon my laptop, if you do it, you're gonna die.
Yeah.
And I'm not special.
I'm just saying I've only seen that happen with Linux machines, right? So not that that's
same
any
as
reason, but I see stuff happening on his monitor, so maybe we're close.
Let's set the duration to 45 minutes, shall we?
Yeah, don't worry about it.
Here we go.
Nice.
No, why? Yeah. Huh?
Just go with it.
No, I can't. It's.
Yeah, no, that's not the problem. The problem is that the other half is on his laptop monitor.
Okay. Okay. So now we're gonna do it. We're gonna do it the old school way. So here we are.
We're
not doing
not
anything because this thing sucks. So. Windows. That's it.
I don't know. You probably have time.
So.
All right.
We've got something here, and we'll have to go.
Nice.
So, that's always the thing. If you, I looked up what tool should I use. There are a lot of ones you can buy, and yeah, this one is open source, and of course I love open source. So I use that, and never with a second monitor, because of course I never thought about that. So, yes, it's about amateur telescope making. First of all, what I often hear when I tell some, I'm at the People's Observatory of Munich. I did also some research in astronomy, and so I'm involved, and I do. I show people the observatory. I explain them how telescopes work, and when I tell them, look, you can make a telescope yourself. Yeah, of course. I mean, it's an optical precision instrument. You have to have expensive machinery. You have to know a lot about optics and stuff like that. Well, yeah, no. Because you need the expensive machinery if you are going to do it with a machine. So if you're going to go huge, of course you're going to need a machine, because we're talking about removing tons of glass here. But there's a big, big but. That sounds wrong. If you're going to do it by hand, and we're talking about telescopes roughly in the range up to a meter diameter, imagine that. That's a huge telescope. That's a big-ass telescope. You can do it by hand. It's a lot of work, but you can do it with the mere attribute of a human being not being able to repeat emotion again and again, the same way, the exact same way. Especially if you tell the people, look, embrace the randomness, you can do it. You can make a telescope that beats manufactured telescopes you can buy, and you can pay a lot of money for it. So here, that's a short outline. So if you have more questions, write me an email, Twitter, whatever. Come to me personally. Although we don't have that much time, I can talk to you about anything you want. I can tell you where you can get the stuff, and if you are interested, hit me up, and I will share all the knowledge with you. Because again, the knowledge I got, I'm not the best guy there is. I happen to live in the same city with the best guy there is in Germany. And if he's watching, and I'm sure he's watching, thank you, Stathis, for showing me that and for making it possible that I can make my own telescopes. I haven't finished a single one yet, because I always rework stuff 3 or 4 times, including those slides here. So, why do I need a telescope? I mean, I can go out in the dark. Dark is a very important part of it. Astronomy works better if you can see the stars. Except radio astronomy, but we're not talking that here. We're talking optical astronomy. Why would I need that? I mean, I do have an eye. I can see the stars. I can see the Milky Way. It's an impressive view. And I know people who, because it was such a nice view, it was a clear night, it was lovely, they went outside, they carried the telescope, they assembled their telescope on site and thought, well, screw it. I'm going to lie down on the grass and have a look at the sky and enjoy it. That's it. That's about amateur astronomy. You love to do it. And, well, if that works for you, go for it. And if you make a telescope, don't let anyone tell you, oh, that doesn't work. If you know it works for you, do it. It's the most important thing. You can make it like you want. So, here are some incentives. First of all, with a telescope, you can have a look at galaxies. Like that one. This one is also from a ground-based telescope, but as you can see, those guys, well, they do it for a living. The ESO is the European Southern Observatory. So you won't see that in a telescope, but you can see a faint blob. You will see that region here. If you don't like that, well, then I have bad news for you. There are better objects, like Albireo here. This is a double star, and this is a star, you can see it with the naked eye, but in the telescope it resolves to 2 stars orbiting each other. You don't see the orbiting, obviously. And the one is blue, the one's red. So here you can see astronomy. If you had astronomy in school, you had astronomy at university, they tell you, yeah, some stars are red, some stars are blue. Yeah, wow. If you see it in a telescope, then it's something completely different. The more you know, the more this experience on the eyepiece is enhanced. And planets. Okay, that's Pluto, sorry. Old habits die hard. Planets. This one is actually what you would see, of course, not that detailed, because there's still an atmosphere in between, and those are probably some 1,000 pictures. No, that's Hubble, screw that. So you can get those quality pictures, similar quality pictures with an amateur telescope, but you need to take a video, you cut out parts which are good, which you like. There's software for that, of course. And you end up stacking like 2,000 or 3,000 pictures, and then you get good quality. It will be, if you have a look at it yourself, it will be a bit blurrier, but you will definitely see the stripes and the big red spot. Fun fact, this big red spot is twice the size of the Earth. So big is quite a good name for it, I think. Yeah, let's go back. So you need light. You need to, what the telescope does, it enhances your sight, your eyesight. It doesn't make wavelengths visible you don't see, but it can make light and regions visible you don't see because it collects light, it bundles up the light. So how do you do that? Well, there is the classical method, as you saw, a lens. Light comes in, focus comes out. You can't explain that. Well, actually, we can. But that's how this thing works. Everybody who wears glasses, who has used a binocular, or whatever you do, that's the main principle. And that's what most people imagine when they think about a telescope. Then again, mirrors. Mirrors have one huge advantage. You have to use only one surface. So they're cheaper manufacturing. You can support them from the back. They're easier to build. So nowadays, mirrors are the way to go. Doesn't matter how big. If you make a 6-inch telescope or a 8-meter telescope, like the VLT is, or a 40-meter telescope, like the ELT is going to be. Let's see that. I would love to see that 40-meter telescope. I mean, that's astronomy porn. I mean, we're talking hot stuff here. What this telescope does is basically you have one main component, that's a Newton, as you can see, and by the curvature of the mirror, of the main mirror, let's call it M1 here. Mirror 1, mirror 2. You can imagine how this works. You basically bend the light in one direction. You focus it in one direction, and then you have the eyepiece or the camera there, or whatever you want, or your cooking stove, and you cook your pasta if the mirror is big enough and you have the sun. So that's how it works, the basic concept. But now, since I mentioned basics, let's go to the basics. These are some circles. Some colored circles. What they represent is here, imagine that being 7 millimeters. That's the eye opening of a healthy young adult at extreme low light conditions. So that's the maximum your eye can open up. And if you go above 30, I have bad news for you. That's not going to be 7 millimeters. It's going to decrease with age. People of the age of 60, 70, they're talking 5 millimeters. So you can see, well, okay, that's surprisingly big. If you actually, I did that, I drawed it actually with millimeters and scaled it down to fit in the slide. And whoa, that's big. Yes, it is, surprisingly big, but it's bigger. The circle next to that is represents a 50 millimeter optical, 50 millimeter aperture. So This is the cheap telescope you're going to buy your kid for 100 euros. Please don't do that. The mechanics are crap most of the time. So kids end up being frustrated and driven away from astronomy just because of that. And binoculars are the same diameter. So you can buy for 100 euros really, really decent binoculars with 2 times this aperture and have a look at the sky. It's not expensive hobby. It's really, really good. What you can see, and people put aside their big telescopes and use the binoculars. Every telescope has its own sky. You see different things, different magnifications, and I mean, it's really, really. You can start small. That's what I want to say here. Then we have a 140 millimeter. That's a typical starter telescope, and this here, this is no moon. This is a 1 meter mirror. It doesn't fit into the slide. So, as you can see, most of you already know it, but the surface area grows exponential. So, you increase the diameter by 2, and as you can see here, the surface goes up by 4. So, in the end, you collect more and more light. And light is extremely important here, because you're trying to get the last photon out of that object, or the last photon that hits Earth. Another thing is that with diameter, you also increase the resolution. So here, that's the so-called baseline. Actually, to increase the resolution, you don't need that part. That part simply collects light. You could just use the part on the left edge and on the right edge, and you would have that increased angular resolution. And in fact, we're doing that. It's called interferometric astronomy. It works great with radio telescopes, but with optical telescopes, they're right about bringing it to functionality. But it's still a bumpy road to go down. A bumpy road, sorry. Sorry, I'm totally on caffeine. And you know how it is. Big audience, you get bright light in your eyes and you barely can see the people down there. And that's how it goes. So it goes inverse proportional. Yeah. So again, the types of telescopes, how it works. Here, the light goes in from the front, and because it's a mirror and it's reflected, you do have to have that part here, this secondary mirror, which goes up. And here you have a typical single lens telescope. You can see you have color errors here, but that's not the point. The point is, what I want to make is, here you have 2 surfaces, here you have 1. One surface doesn't have to comply with anything. You can have one surface, you can make it work, and at the moment it works, it works. Here, you have to make 2 surfaces work with each other. And that's much, much harder. Because if you happen to make it wrong, it can totally go south. If those 2 are not centered properly, the whole optical capabilities of the telescope go really, really bad. So, yeah. Now to the main part, making the telescope, actually doing it. First of all, I will talk about the optics. This is the part which is most complicated, I'd say complicated is the wrong word. Less people are familiar with optics than they are with making aligning wood so that something works. So that's the new part for most of you, I guess. I happen to know that at least one person in the audience is already thinking about making a telescope, so he maybe knows more about that. But it's not complicated, it's not hard. What would you do? What would you make your own telescope? I skipped a slide. Well, basically, because you are flexible, you can make it the way you want. If you want to make a telescope that's pink, you can make a telescope that's pink. If you want to make a telescope that's rubbish, you can make a telescope that's rubbish. You can make it however you like. And you can also include rocket launchers, which was suggested by somebody. But I wouldn't recommend. Most other astronomers don't like a rocket launcher being on your telescope and destroying their hard work. And the quality, again, if you want to make it, you can make it as good as you want. You can go through n+1 iterations and still add another one. You don't care. Okay, you care because at one point you want to use it actually and make something with it, but that's where I'm stuck. I'm making the iterations. I started writing my mirror from scratch 2 times now. So you can adjust that part. If you need a telescope that's only going to work for infrared light because you want to make an infrared transmission path, go for it. You don't need to invest that much time in it. You just need polish it roughly, and it works. You don't have that high specs as you have in with optical light. The price, of course. Although a small disclaimer here: if you're going to make a telescope 10-inch big and you want to save money, don't do it. You can buy really decent telescopes nowadays with up to 16-inch, and you would still save money. I'm talking about raw costs here, not the time invested. If you calculate that, it goes through the roof. I'm talking about cash you take in your hand and put on the counter. You will save money up to 16-inch, but make a small telescope, one that you would like to use, of course, to gain the experience, to see how it is, how it works, where the problems are, and then go big. If you go really big, if you go above 18, 20, 24, 30, 33 inches, 40 inches, the sky's the limit here. People are running amateur telescopes with 1 meter diameter. That's insane. If a guy arrives at the site with a trailer and he tells you, yeah, that thing is full with a telescope, with 1 single telescope, and you have to climb up a ladder 2.5 meters to get to the eyepiece, you know what I'm talking, why I say it's insane. It's crazy. But then again, we are at the Hacker Congress between the holidays. I guess we are crazy too. And, of course, availability. Telescopes above 18-inch, light construction, that you can carry it with one person, that's considered light there. They're not that abundant. There are some small manufacturers, and you order it today, you will have it at the 33rd C3, maybe. So we're talking 2 years delivery time, and in that time, of course, you will be able to make your own telescope. And most importantly, because you freaking can. All those outlines are basically, why should I build my own 3D printer? Okay, back in the day, like 2 years ago, you had no option. You had to build it yourself. But nowadays, in Germany at least, you pay 500, 700 euros and you get a decent one. No, not the best one, and still it has issues, but you get a good one. But many people still do it. They build their own 3D printers. There's Linux from scratch. I think I still don't understand, but maybe that's my lack of understanding there. But still, people do things themselves. And that's always the reason. Because I want it better, I want it now, I want it however I want. And that's here. So, the shopping list. So, you say, cool, I want to do that. And you start and you say, well, I want to go to the hardware store and get the stuff. So what you need is a piece of glass. A small disclaimer here, you need special glass. Not always. If you make small telescopes, I know a guy who made his 2 really small telescopes, 4-inch, with standard window glass, which is a nightmare if you do it. But it's okay, I guess, for that size. And it's cheap. It's definitely cheap. He paid exactly nothing for it. I mean, we're talking 4-inch here. That's this size. That's a piece of glass you get from the junk. I mean, from the scrap. It's like, yeah, you can get that. Nobody cares about that size of glass. Then you need a tool. That tool can be another piece of glass, can be granite, can be ceramics, can be a composite construction that you take 2 plates or 2 bathroom tiles, you glue them together, you put them together with some cement or some clay or whatever you find, and seal it around. That's the important part. If you want to start it, Google, or ask me, or you can write me and I can tell you where to Google, where you will find your tips and where you find your materials, because many, many details are omitted here. Like 99% of the details are omitted here. Some sand, silicon carbide actually, but that's, yeah, we call it, you take 2 pieces of glass, throw bits of sand in it, and then you have a telescope. That's how one guy put it once when we discussed it at a astronomy meeting. And polishing agent, that's most of the time that's not aluminum oxide, ceroxide. Really interesting chemistry going on there, and nobody really knowing why. If somebody in the audience, and that's me asking somebody for help, knows how ceroxide works, how it polishes glass, come up, you're gonna get a mate. Really, I really had a hard time to research that. And pitch, like the black thing pitch, not the tone one. So, here we have that's the mirror, that's the tool. Here I illustrated 2 pieces of glass because I was lazy, pure laziness here. What you do is you have those 2 mirrors. In between there's the sand, those 2 pieces of glass. Here's the sand, the abrasive, and here you put pressure on it. So what happens? In the center of the top part, you have higher pressure, and on the edge of the bottom part, you have increased pressure. So, hands up, and I want you to participate on that. What will happen with the top part? Yes?
You wrote the middle. You wrote the middle.
You wrote the middle. You're gonna get a hole in the middle. Oh, do you remember the slide from back there where we had that concave mirror? Well, that's what happens. You get the curvature. And if you do that chaotically enough, so you turn the 2 parts in opposite directions randomly, like you make some. Actually, I wanted to make a small demonstration here today, but guess what? Where that demonstration is exactly at home, where it's absolute with a perfect use. So you rotate it, you move it along, you make different lines, you make overall a chaotic movement, and you end up with a sphere. So what you do then is you measure how deep you are, and you know the shape of the sphere you have, and if you get to a point where it is the shape you wanted, you refine it. First of all, with silicon carbide, you start with with a granule size of 60. Oh, by the way, silicon carbide, everybody knows it. It's the stuff glued on sandpaper. And you go up to 320 granule size, and then you go to aluminum oxide. That's a really fun fact. So I was traveling. Traveling around in Munich, taking the metro, and well, as chance will have it, I forgot my wallet at home. In the wallet, it was my student ticket. So basically, I got checked. Of course, when you forget it at home, they check you. They ask you where's your ticket, and then you never mind. So sometimes it happens that the police is present. So imagine a police officer. Oh, tell me, what's in the backpack? They're actually allowed to do that. What's in the backpack? And I just got my mirror, and there is also some polishing agents, some silicon carbide, some aluminum oxide, and whoever knows what color aluminum oxide is. Pure white. And then imagine that being a powder with the size of 9 micrometers. That guy started asking questions. Thank God they had like a rapid test, and I told him, look guys, you see that's a set, that's the 80 granule size, that's silicon carbide, that's why it's black, it's silicon, it has, and I explained, and then they believed me, but still, it got complicated. Sorry, I didn't understand. I really, honestly don't hear what you're saying. Is the mic on?
I just said you can be very lucky that I didn't ask you for a bioassay, that you didn't have to try out the powder and put it into your body somewhere.
Actually, yes. There's some research coming up about what aluminum does to your body. It basically screws up everything. But so don't inhale it. That's a bad idea. Okay? So then you with all these steps, you go finer and finer. You refine the surface. Starting with the 32 micrometer aluminum oxide, you can already see, if you look at a flat angle on the mirror, you can see it starts reflecting. That's where you get, oh God, yes, I'm close to having a mirror. No, you're not. Then the work comes in. This guy here who's putting the polishing agent on, that's the copyright holder, Stathis Kafalis. That's the guy who's like the guru in Germany, in my eyes, my opinion. But he knows a lot about grinding mirrors. And I know he's watching, so I know he's probably going red right now, but I don't care about that. So, what you need is cerium oxide and pitch. That black thing, you know why they call it pitch black? Well, there you see it. And this yellowish powder, which was also a funny thing, they wanted to test that too. You dissolve it in water and you put it on the pitch, and you don't put a lot in it. That here is really, you see how thin it is? You don't put a lot in it, but still, the cerium oxide kind of interacts chemically with the glass. Then again, it beds itself in the pitch, and kind of like millions and millions of razors cuts the glass away and polishes it away, and kind of smears it. Also, there is some theory. I found a paper by some Chinese researchers, which I dare not. I don't know a lot about that stuff, but I don't actually believe it. That there is also some thermal processes going on, heating the glass up and smearing it away. I honestly have no idea. Those Chinese guys who wrote a paper, I don't believe, have more credibility than me in that matter. So, then you need to test it. All the process is, there are iterations. You do something, you see what this something does, and then you look again, and you see what this something does again, and so on and so on. First of all, you want to find out how deep is a mirror. What is the shape of my sphere? That's how you do it. You take a ruler and measure that distance. Fairly easy, isn't it? No high-tech involved here. The more high-techy way, high-techy, whatever, high-tech in terms of the 17th century, is you take a torch, you make the mirror wet, you take a torch and you look where the reflection goes, and if you hit the right spot, you will know that if you hit it, believe me. You measure that distance, and you have the radius of the sphere that this surface is an element of. Sounds complicated? It isn't. It's really basic geometry. Because a spherical mirror will reflect everything that comes from the center back to the center. That's what we use to make the fine testing with the Foucault testing. Léon Foucault, most people know him of the Foucault pendulum, but this is also an ingenious method of making high precision measurements on mirrors and reflecting surfaces in general with minimum monetary involvement. You are talking to make a Foucault tester. We're talking, if you are going to go fancy, like really fancy, we're talking 50 euros here. You can make it actually for free if you go to a scrapyard or something like that. It's really, you can make it really cheap, and it's really precise. It's surprisingly precise. And then again, interferometry, that's like the more techie way. I won't illuminate interferometry here. I could make a talk on interferometry alone, or interferometrical testing of mirrors, because you have to take into account so many effects that I'd simply say that's nothing for the beginner. But if you go, there's a lot of information on that to read up. So Google it. You will be more than happy with information you will get. We'll get there. So here we have a Foucault tester. On the bottom, you see the light source shining onto a mirror, projecting the light on your test subject. And here you have an edge, a knife edge. That's why it's called also Foucault knife edge testing. And here what you can see illuminated is, so basically what's the thought behind this? Here we are roughly in the center of the mirror. We are talking, here the dimensions are scaled down in order, that's a Wikipedia picture, in order for it to be, for you to be able to understand it. But that size, if compared to human eye, that mirror would be there. That would be a typical focal distance for that one. So here we are roughly in the center. So what you do is you know, okay, if I project something from the center on the mirror, it goes back to the center on a single point. So if I put a knife edge there, a really, really sharp edge, which blocks which binary blocks or allows light to pass through, if I had a perfect sphere, a perfect setup, theoretically, I would see the mirror or the test subject illuminated, and then it goes black as I move the edge back and forth. Well, reality kicks in, and you get deviations from the sphere. So here, that's more or less a good sphere. Here you can already see, here you have kind of something funny going on here on the edge. Here there's a kind of a mountain in the center, here a smaller mountain combined with a ruined edge, I'd say. Here you see some shadings, here you see a pit in the middle, and again this edge. This is a typical error beginners make. Nothing you can't correct, but yeah. So this is what you would see. And you see here, these deviations from the sphere we're talking about maybe here it's huge. We're talking about 200 nanometers? Nanometers. Excuse me. 20 wavelengths. Sorry. 20 so lambda 20. I'm sorry. Yeah. So this is 20 wavelengths, and as a matter what you would use as wavelength, typically white light. So you would use that's 20 times 400 nanometers. That's a deviation here. We're talking about precise testing. Actually, I don't know if I do have that picture where you have that Foucault test, and somebody puts a hand in the beam. You can actually see the thermal turbulences of the hand. So you can imagine what the resolution here is. It's really, really good. And yeah, interferometers. This is basically for you to have something to Google. Those are interferometers which work with, which amateurs have built, common path interferometers. They are not that precise, but they have an advantage in construction. So that's basically for you, if you want to look it up, that's what you would Google for: bath interferometer, point diffraction interferometer, and the Fizeau, which is also point diffraction interferometer, but with a special setup. Again, I could go on. I didn't exactly lie to you, but I didn't tell the whole truth. The sphere does not provide a perfect image. If you have light coming from infinity, here we have an illustration. If you have light coming from infinity, here parallel beams, that always helps shaking up batteries. So here you see, that's the focal region. That's called spherical aberration. You have it always with spherical optical elements. They kind of have a hard time into focusing light from infinity onto one point. And correcting this is fairly easy. You just take your sphere. This is a bit exaggerated, but you take your sphere and make a little dimple in the middle, and you end up with a parabola, and a parabola focuses all the light on one point, coming from infinity. Again, this is really, really exaggerated. Car lights use that inverse path. You have the light bulb here, and you get a parallel path there. Parabolic antennas, guess where they got the name from? So testing that is kind of a bigger challenge, because you don't test the whole mirror as a whole, and you only know how to test spheres. So what we do is we cover up some areas there. It's called a mask. You have black paper and you cut holes in it. So what you do is you approximate that parabola with a lot and lots and lots of, depending on how many you want. For a small mirror, 3 regions. For a big one, you would use up to 8, up to 10, 12. I've seen one with 14. That's just insane. So you approximate the mirror with zones. You assume that you have a steady curve. You don't make funny stuff between the regions. So what you do is you measure a lot of spheres, and if the relations of the spheres to each other is correct, everything works fine. There's also software where you can calculate what that relation has to be, which fits everything and stuff like that. You can do that in an Excel sheet or LibreOffice Calc sheet. Whatever you want, you can do that. There's a lot of software, and if you search for core interferometry, you will stumble upon those pieces of software. Most of it runs on Windows, but Wine works just fine. So this is the grinding part, making the mirror. For a 8-inch, 200 millimeter, 8-inch or 200 millimeter mirror, we would calculate, if you are good, 90 hours of grinding, polishing and everything included, and testing. If you are average, we're talking rather about 130 to 150 hours. The biggest part is building the telescope. First of all, you have to decide, what do I want? Do I want a telescope which I want to, perfectly possible with an 8-inch, to take it with you on the airplane, hand luggage. I don't know if the TSA likes it because I don't know, but I know people who take their telescope on the plane as hand luggage. Maybe you want to, I had a problem. I needed public transport. I didn't have a car until recently. So I needed to carry that telescope with me on public transport. So I bought one, blame on me, but yeah, I bought a small telescope, have that in my backpack, have a tripod in my hand, and the eyepiece is on the other hand, and I just can't go ahead. People can take me easily with them in the car or whatever, so it's not hard for them it's not easy to them for them to say no and just say, okay, I don't want to, I don't have room or whatever. It was really, really compact. And people are even going for a hike with their telescope. So we are talking about really, really lightweight and compact stuff here. But if you want to observe from your backyard, there's no point in investing all the time and the money and the complicated constructions and the many failures or whatever. You just build a telescope that works, and you don't care how heavy it is. You put a plastic sock on it, and it's protected from rain and everything. It's just there. If you want to take pictures with it, there are different demands. So you have to decide, what do I want here? What do I want to build? So let's start with what are the main factors. I mentioned transportability, handling. The best telescope is of no use if you can't use it. That's a tautology. Anyway, and you want it to be rigid. You don't want to invest tons of hours in your optics and making everything perfect, and then everything being sloppy and shaking around. Because that's the main reason. Do you remember those cheap telescopes I told you about? Don't buy too cheap telescopes for kids, because they have sloppy mechanics and they are no fun to use. And if it's no fun to use, you won't use it. And if you won't use it, then don't start in the first place. So those are really important factors. And especially the transportability is a thing. Also, your budget. If you have no budget and if you have no car, there's no point in making a 1 meter telescope. We are talking about 5,000 euros only for the mirror. And if you are not careful, and that guy in the stream watching right now, he knows what I'm talking about. He made an 8, maybe you ruin 400 euros worth of glass. He was nearly done. He was doing his final tests. Had his mirror on a bench, and his kids were in the house. He was eager to finish it. One of the kids opened the door, went through the house, kicked the mirror off the stand, and you had 3 really, really well-polished shards. Yep, that hurts. Another guy, the status guy, I got most pictures from. Thanks for that, by the way. In order to avoid that, he put his foot under the mirror to catch it. He had a broken foot. The mirror was okay. He said it was worth it. Imagine. So, yes, be careful with it and calculate. A failure shouldn't ruin your budget planning for the next holiday. So basically, one thing you have also to decide is how do I want to mount it. Here, this is an alt-azimuth mount, shortened up alt-az. So you see, it's easy. Up and down, left, right. You have 2 axes, perpendicular or parallel to gravity, perfectly fine. Engineering, no challenge. Here we have a German mount. The reason you would do that is you want to take pictures. So the Earth axis is tilted. And what they do here is you have one axis parallel to the Earth axis, and you counteract the movement of the Earth, of the stars, relative to the Earth, of course, and you just move your telescope along. So you just have to worry about one axis being guided properly. That's a huge advantage, trust me on that. You have even there are clockwork, like this clockwork. Old Russian clockwork mounts, which work marvelously. They are great. The only problem is, once you winded them up, again, police. So you are on Tenerife, you have your clockwork. Oh, it's a great night. Tomorrow I'm flying, I don't care. I want to take pictures. So you wind it up. You wind it up a bit too much because you want a bit further than you think you will need. And then on the next day, somebody checks the bags, the luggage, and here's a coming from back. Yep. Explaining. So, actually, you see what shape this thing has? One amateur astronomer, she's a really great person, great humor. And she was on top of a mountain. And she was setting up her telescope, was observing. And nearby there is a military area. One of the residents saw somebody putting a silhouette that looked like that on top of a mountain. So, in German, there is if you observe, you want everything to stay dark, because adaptation to darkness is something that breaks really easily and needs about half an hour to rebuild. So, you avoid light. And there is the term Weißlichtsau, which means white light pig. So she was there on the telescope. They sneaked up on her. We're talking about special ops here, spec ops, sneaking up to her, lighting the whole area. And she just saying, weiß nicht so. And then looking up and seeing guns pointed at her and people screaming, go away from the rocket launcher. So you see, astronomy is a really, really peaceful hobby, but yet again, those are some, that doesn't happen all the time. So I don't want to scare you off here, but I just want to loosen you up. So that's how you would build an alt-as mouth. That's a typical example. So here you have your main mirror, you have two rods, here you have your secondary mirror, your focuser. The focuser is something you can build it yourself, and especially nowadays with 3D printers, you can easily print one for yourself, but you need high precision, and honestly, they don't cost a lot. If you get a really, really fancy one, you're paying 300 euros. But we are talking about really, really fancy stuff. Okay, if you go really big, then it goes really, really expensive. Actually, how much time do I have? 5 minutes? Yes. Holy crap. I mean, I was told, yeah, okay. I have 5 minutes, I'm sorry for that. So, what you can make a truss dop, that's called a Dobsonian. So here is a full tube Dobsonian, that's like kind of the stuff you can buy. This one is really, really heavy. We're talking about, they make, you can separate the pieces here and carry them around because you can't carry that in the whole, I think it's a 14-inch. And yeah, that's a full tube one. Then a truss Dobson. This one is a 32-inch Dobson. 32, yes. So basically what I'm telling you here, that's this one here, the finder, is also a Newtonian telescope. It's just 4.5 inches, but that's the finder. This mirror here, the secondary mirror, has that size. So we're talking about a really decent one, and you can see really nice things with it. Oh no, I stand corrected, 28-inch. Sorry. And again, a truss Dobson, that's a classical design with 8 rods, by the way. And here, this one is meant for photography. So this one has to be really, really sturdy. You don't want your camera, which can be quite heavy here in the front, to move relative to your main mirror. That's really, really bad karma. You don't want to do that. Your picture is going to be ruined. Your half-an-hour luminosity picture is going to be crap. So you want it to be as steady as possible. So that's why it's made like that, with a huge diameter in the middle and going smaller, going thinner outside, because it's also mainly supported in the middle. So here you have a three-rod design, a 2-rod design. This one is really, really, really compact. The rods are separated. You see this here? Those are bass strings. This thing is set up and you can play music with it. Not a good one, but you can play music. And here you have really the baffle in front of the second. So this one is a compromise going totally for transportability. You lose light if you do that, because you have the strings going in the optical path. You have this huge thing here, so you want to have it really light. You're losing light, but you want it to carry it with you. And I happen to know that Stathis has made with his motorcycle a tool with that. And so yeah, everything possible. So the top part I have to speed up a bit. So if you don't understand something, please forgive me on that. So the hat, the top part, has 2 main components which you want to support thoroughly. Here, the secondary mirror, that's the shiny thing there. Guess what? And the focuser. That's one of the fancy ones that costs 200 euros. And you want that hat to be as light as possible because you are away from the center of mass, and you want it to be stable. You see engineering problems coming up? Everybody does. And solving this problem seems impossible, but it's really, really they're really, really good solutions. So here you see trusses here on the supports, and yeah, here another solution on that. And yeah, so you can solve that. People have actually made secondary mirror supports with guitar strings. So everything's possible here. 2 minutes? Over?
It's 2 minutes.
It's maybe 5. I'm speeding up here. Sorry. And here you have the mirror box, which is basically quite easy. You have this structure here, which supports the mirror. Here there would be silicon pads if it's done. And everything movable, easily movable, that everything can align in such a way that there is no torque on the main mirror. You don't want that. You really don't want that. It ruins your image for no particular reason. So you don't want to do that. So here again, the altitude wheels attached to the box and the rods here, and you basically, and all that goes on the rocker box, which is basically Teflon grinding on top of Ebony Star. Ebony Star is a top counter cover, a kitchen top counter cover. So it's easily accessible. They don't produce anymore. There are alternatives. But yeah, so that's how you would do everything. I want to thank those guys, Stathis, Martin, Tassilo, and the People's Observatory. And I want to dedicate this talk to John Dobson, without whom this Dobson design would not have been possible. He died earlier this year, in January last year. So he died earlier this year, and yeah, was a huge loss, definitely, for the community. And that guy was the one that made democratized astronomy for everybody, the sidewalk astronomy. And yeah, some software here. Just Google it up, open source, everything. Download it, modify it, improve it. And some links where, yeah, Cloudy Nights, that's an English forum. Everything is organized with forums in the sector. Astrotreff and Astronomie.de are sites that are German, so everything happens in German. And yeah, can we arrange 5 minutes for a Q&A?
Yeah, I think that's possible.
No, thank you.
Yeah, sure. Yeah, so if anyone has questions, just come to one of the 4 microphones and we'll just go ahead with microphone 3.
Hi, I was curious. Hello. I was curious whether amateur astronomers using these systems have ever done things like calculate redshift, and whether they actually look into the more sort of scientific side, or whether it's purely observing.
There is some science done, but it's mainly variable stars and asteroids and planetoids, stuff like that. Because the problem with, you could possibly calculate or measure redshifts, but the matter with that is you need for redshift calculation, you need high resolution spectrometers, and those are expensive, and they are expensive for a reason, so they're really, really hard to make. So yeah, to calculate redshift is kind of a hard thing, and you can only, spectrometers need a lot of light, so you can only do that on bright objects, and all the bright objects have already been measured. There's the hell measured out of them. So you can do that, but you can't contribute in science with that. Main contributions of amateurs are, again, as I told you, small planetoids and variable stars. But there's also one site called galaxyzoo.com, where you have pictures of galaxies, and you can sit there on your PC. Works great if you have to wait on somebody. You can say, okay, that's a spiral galaxy type, and so on. So you can help classify galaxies there. So, you're welcome. Yes, please, mic number 2.
Hello?
Yes?
If you're using purely glass for the mirror, without the shiny surface known for the bathroom, isn't there a big loss of light?
Yes, it is. You have to cover it up. I completely forgot that in my talk, and I forgot that completely. Thank you for pointing that out. You have to send it somewhere. You need a vacuum chamber to illuminize it, and to put also a cover material on top. Silicon oxide, so that you have that sealed. But you can do it also at home. There's a chemical reaction which drops out elemental silver, and you can cover that in silver. But it produces hydrogen, and hydrogen is kind of an explosive matter. So you want to be careful with that. Mic number 3.
I just wanted to mention, you mentioned Dobson at the end. So I just wanted to mention something. The funny thing with Dobson is he started astronomy because he was converting to Hinduism. And the funny thing is Hinduism has, where we all know Christian Kreationisten. The funny, with the 7,000 years old, the problem with Hindus is they have the exact different problem. They have an universe that is billions of years old. And so one of the reasons he tried this one was to get people for a steady state universe model. And so I think it's something to show that, well, be a little bit tolerant to religious people. They may be idiots quite often, but well, sometimes you get a nice outbreak from it.
I happen to have seen an interview where he said that this Big Bang theory thing is a complete, and we're not talking the show here. That's bogus. He said that. True. But he made a huge contribution to science.
I just wanted to say, because we had a problem with some...
because we're running tight on schedule, maybe you're... thank you for sharing that with us, I
have a question. You said you cannot use regular glass, so what kind of glass are you supposed to buy? You
want to use glass that has that doesn't expand as much with thermal differences, because you want your mirror to cool down smoothly, so you don't have bumps and ridges building up just because the glass is expanding or cooling down. Because you have to imagine you are carrying this telescope from a 20°C perfect environment to, if you are not lucky, to a minus 10 degree environment, and even with that special glass, you need to wait some time until the mirror has cooled down enough that you can observe. It's really that's the whole thing. And if you make small telescopes, you can use thin sheets of glass, normal floating glass for windows, and then again thin sheets cool down easily, and you have no problem at all. So that's the only reason.
What is it called, the glass you use?
It's called BK7, it's called Pyrex. There are many, it's basically most of the time it's floating glass, so there are many trademarks on it. But the way I would buy glass for that is hit up a guy who sells glass for those purposes. There are many, and it's not really it's not that expensive. Okay, so I think that was it with the questions.
Looks like it. Yeah, thank you again.